MALDI, Digital Ion Trap Mass Spectrometer, which is a very intriguing title to me. So Ryan, if you're ready, I'll hand it over to you.
Okay, can everybody hear me okay?
Yes, we can hear you.
Excellent. Okay, thank you very much for the introduction. So today I'll be talking about our MALDI Mini Digital Ion Trap and looking at some proteomic applications we've done. This is a new instrument for Shimadzu, and it's one of the first commercially available digital ion traps. And so I'd like to kind of just start off briefly with the overview of the presentation. So I'll kind of talk about the origins of the digital ion trap, and then kind of give you an idea of what the differences between conventional ion traps and digital ion traps are, and then talk about Shimadzu's journey to create the MALDI digital ion trap, and then we'll kind of look at some of the applications we have. So basic proteomics, some glycomics, and also some antibody drug conjugate work. And then I'll kind of conclude with a summary and my acknowledgements. So to start off with the origins, this is kind of an abbreviated timeline, but the first rectangular waveform and duty cycle that were used to operate a mass analyzer was first done by Dr. Richards in 1973. And then sometime after that, in 2001, Dr. Ding demonstrated that mass analysis could be performed with a 3D digital ion trap that operated by scanning the frequency. And so this was a pretty significant discovery as far as it goes for Shimadzu. Dr. Ding works for the Shimadzu Research Corporation in the UK. And then in 2007, the Tanaka group from Shimadzu Corporate in Kyoto, Japan, reported using a digital ion trap mass spectrometer, which was driven by a high voltage rectangular waveform and trapping ions, and developed several different DIT-based mass spectrometers. And so lastly, last year at ASMS in 2019, we released the MALDI Mini, which is the MALDI digital ion trap for the first time. And so it's been on the market for a little bit now, and we have some good data to show. And so what are the differences between the digital ion trap and a conventional ion trap? And so the first thing is that the rectangular waveform scans the frequency. And so if you can see in the bottom right-hand corner, you can see how the waveform is rectangular, and you scan the frequency. And then a traditional ion trap uses a sinusoidal waveform and scans through the voltage. And so that's one of the main differences between the two. And then because with the power supply voltage, the RF is significant, the voltage is significantly lower for the RF in the digital ion trap in comparison to a conventional ion trap. And then also scanning the frequency with the rectangular waveform allows the ion trap to operate across a larger mass range, whereas in the sinusoidal waveform, you have a limited mass range because it operates at a fixed frequency. And so these are just some, basic differences that would help the user to kind of understand, what are the differences between what a traditional ion trap offers versus a digital one. And then so some of the basic advantages that you would see with a digital ion trap is the RF frequency modulation allows for ions to be trapped over a very wide mass range. And so that's kind of important when you want to analyze larger molecules as well as small molecules. And then the DIT also provides the ability to trap millions of ions essentially at any value of M over Z. So you're able to trap and analyze a lot of molecules when looking at different samples. And then the DIT permits mass analysis of the entire range of singly charged intact proteins or molecules, and it gives really excellent signal to noise. And since we're talking about a MALDI, this is actually pretty critical because when you're ionizing with a MALDI system, obviously we use a matrix, and typically that's in high concentration. And so that can tend to suppress some of the signals you may want to analyze. And so by having this ability to remove the matrix ions that would kind of suppress other signals, you're able to get better signal to noise. And then so our path to the digital ion trap actually started back in 2002 with our first offering, which was the Axima QIT. So basically this design that I have in the top left-hand corner is of the Axima QIT, and you can see that there is a quadrupole ion trap there. And so that's one of the first components that was designed with that instrument. And then later it was perfected in our Axima resonance system, which is released in 2009. And then so now you can see how large those floor standing models are. And now at this day and age in ASMS in 2019, we released the Multi Mini. And as you can see, it has a very, very small size, and it's very, very compact. And you can see all the different components in the top right-hand corner of the screen, where you can see how much smaller the space it takes up and how easily it achieves what it needs to do. And so to give you kind of a basic background on the Multi Mini 1, the size of the instrument is minuscule. The footprint's equal to an A3 size of paper, so that's rather small, as you can see on the right. And typically with Multi, we have a simple, straightforward sample preparation where you're just applying matrix and the molecules of interest to the target and allow that to dry prior to ablation with the laser. And so the instrument uses an ND-YLF laser with 349 nanometers. And so that's kind of important because that helps us to better ionize the molecules that we want to analyze. And then for the mass range of the instrument, it goes from 650 to 70,000 Daltons. And then in the MS2 and MS3 range, it goes from 350 to 5,000 Daltons. So it's fairly good size mass range in order to analyze lots of different types of molecules. And then the Multi Mini 1 can operate in 3 different modes. You have the MS1 mode, MS2, and also MS3. And then to be able to fragment molecules, it uses helium and or argon. For collision-induced dissociation, you can select between the two. And so this is just an example of one of the proteomics applications where we look at the intact mass spectrum of BSA at 250 femtomole. And so as you can see, it's a pretty broad mass range from 10,000 to 70,000, and we can detect the singly charged, doubly, triply, and quadruply charged from BSA. And so the signal to noise, as you can see in this mass spectrum, is pretty good, and it's easy to identify the peaks of interest. And then so also we looked at a triptych digest of BSA, and the top mass spectrum, you can see a series of peptides. And basically we isolated some of those peptides for MS-MS analysis, and we were able to fragment them successfully and be able to get their sequence. And then by comparing them to the mascot database, we're able to show that we can identify serum albumin and also the sequences for those peptides. And so this will allow you to do kind of routine proteomics workflows and be able to identify amino acid sequences. And then so moving on to glycomics, kind of changing gears, we have a basic example here where we have a glycopeptide with a O-linked oligosaccharide. And so basically we start out with our MS first, and we can see the intact mass, and then we fragment it in the MS-MS, and we can begin to start to see the individual sugars that make up the oligosaccharide. And so the triangle represents dioxyhexose, the circle represents hexose, and the square represents N-acetyl hexosamine. And so basically, if you're looking at the MS-MS spectra, you can see that we can start at the bottom of the actual molecule itself, and you can see there's the triangle, square, and circle. And so it fragments well, and you can begin to work out the structure of the oligosaccharides that is attached to the peptide. And then if we go to the MS3 and look at the peptide backbone, we can begin to identify the amino acid sequence. And so this is very valuable to look at, one, the actual oligosaccharides attached to the peptide, and then also understand the sequence and where the oligosaccharide is attached to. And then also we worked with N-linked glycans that were actually from immunoglobulins. So the immunoglobulin was digested with trypsin, and so we get an MS spectra of peptides that come from that immunoglobulin. And then in the MS-MS mode, again, we're able to look at deoxyhexose, hexose, and the N-acetyl hexosamine. And so the first MS-MS, we're able to see some of the sugars that are present on in the oligosaccharide. And then with the MS to the 3, we select one of the precursors, and we're able to kind of look at the branching that's occurring and get a better idea of the structure of this particular oligosaccharide. And so another interesting application that we had was we basically enriched a glycopeptides that came from a monoclonal antibody. And so this mass spectrum represents the mixture of the glycopeptides. And so in order to look at one of these individual peptides and kind of get an idea of the sugars that are attached to it, we're looking at peptides that have hexose and also N-acetylhexosamine again. And we selected the 2796.3 peak, which you can see in red there in the center. And so then we fragmented it in the MSMS mode. And so basically what we were able to see by this MSMS spectra is we can see the variety of the different sugars or glycans that are attached. And so first we started out with fragmenting the peptide backbone so that we can get an understanding of the amino acid sequence that's involved. And then we chose to also look at the, it's really difficult to see, but it's the 1272.7 peak, and look at a kind of a fragment of the N-acetylhexosamine. And so when we compare these two on the, compare the MS3 spectra from these two, first we have the precursor of the peptide backbone, which is 1189.7 at the top. And so that gives us kind of the fragmentation in the Y ions from the peptide sequence. And so we can see that. And then when we look at the MS3 spectra for 1272, which has that fragment of the N-acetylhexosamine, what we notice is we first start to see that we have some peaks that are similar, but then we begin to notice that there's a shift of 83 Daltons. And so what we can learn from that is that this glycan is N-linked, and then we can see that it relates to the other amino acids that come from the Y5, Y6, Y7, and Y8. And so that's kind of a quick and fast way of identifying kind of the binding site of the glycan to the glycopeptide. And then in addition to identifying one of the oligosaccharides, we also were able to follow the same exact method and analyze 8 different ones and be able to determine their structure. So this is a very powerful tool in order to look at these individual oligosaccharides, which are actually rather important because, as you know, oligosaccharides are post-translational modifications that are put onto proteins, and they regulate the protein's function. And so due to the heterogeneity of most oligosaccharides, it can be difficult to determine what their structure are because it's not known from the genome. And so to be able to identify them and understand how that structure relates to the function of the molecules is very important. And so this can be a useful tool for anybody that wants to study glycomics. And so basically, just to give you kind of a summary of the results, when analyzing an enriched fraction of tryptically digested antibody, we were able to observe multiple glycopeptides. And then we obviously analyzed one peptide further, the 2796, and that was analyzed by MS2 and MS3 in order to determine the structure of the bound oligosaccharide. Additionally, we were able to determine the amino acid sequence, which is pretty important for determining where the linkage is. And then lastly, fragmentation through MS2 and MS3 experiments is kind of key, generating data that's fast and accurate for structural elucidation. And we kind of demonstrated that with both the N and O linked oligosaccharides. And so moving right along, we're gonna kind of sidestep and talk about drug antibody conjugate analysis. And so essentially, just to give a basic background, ADCs are monoclonal antibodies that have biologically active drug molecules attached to them. The reason why this is important is because ADCs are highly selective and they have effective low molecular weight drug compounds, and this is useful in treating certain types of cancer and giving you a targeted approach to affect very specific cells instead of a broad area. And so it limits the number of side effects. And so that's really an important feature of these types of molecules, and they pose a very important position in the future. And so to be able to analyze them and understand their structure and actually how much drug molecule there is rather important. And so basically we took a a regular monoclonal antibody, which had a tryptophan residue on it, and we attached a fluorescent AMBO molecule. And so essentially you can see the structure of the monoclonal antibody with the tryptophan residue and the side chain that's bound to it after a reaction. And then on the bottom right-hand corner of the screen, we have the amino acid sequence. And so essentially what we're trying to do is, one, be able to identify the peptides where this side chain is bound, and then also be able to, determine where it's actually connected. And then so the first thing that we were able to do was comparing the naked monoclonal antibody with the derivatized one. And so when we take these two mass spectra and we overlay them, we can see the differences between the two. And so from this, we picked out two separate peptides which we wanted to fragment in order to give us kind of better structure elucidation. And so the first one that we did was the 2416.9. And so this was the MS-MS spectra from that precursor. And so in this, we were able to identify the peptide backbone, and then we also see a shift that determines the side group that we put on the actual antibody itself. And so from this, we were able to then do the MS to the third, and we can compare the naked monoclonal antibody again with the one that's derivatized. And so we can see that we're able to identify a lot of the Y and some of the B ions for this particular sequence. And then when we run our data against the mascot database, we're able to get sequence information and also determine the protein that that's related to. So this gives us a good tool to be able to identify the peptide sequence and kind of confirm that the sequence that we expected this derivatization to be bound to, that we were able to confirm that. And then again, going back to the original two spectra, we decided to look at another peak, so the 2560.9. And so with that, when doing the MS-MS, we were able to, again, identify where the peptide backbone is. That's 1808.0. And then we could also see the derivatized molecule that we put on the monoclonal antibody, as well as a piece of that derivatization as well. And so from there, we did our MS to the 3. And again, following the same kind of workflows before, we compared the naked NIST monoclonal antibody to the derivatized one, and we're able to match the some of the Y and B ions for this particular peptide, again confirming the location where we thought the actual derivatized molecule would be. And then when comparing that to the mascot database, again we're able to gain the amino acid sequence and also identify the monoclonal antibody. And then so the results of these kind of experiments, we're able to do mass spectral comparison of digested native and derivatized NIST maps, enabling identification of the peptides with the attached ME fluorescein group. And then the MS for the 2416.9 precursor shows prominent neutral loss, which was assigned to the ME fluorescein group. And the MS to the third resultant fragments allowed us to determine the amino acid sequence. And then similar approach was applied to the second peptide that I had shown, the 2560.9. And again, we used the MS-MS to define the similar neutral loss that corresponds to the ME fluorescein. And then the MS to the 3 was again used to fragment the 1808.1, which allowed us to confirm the amino acid sequence. And so with that, I would like to say, thank you, and I would like to acknowledge the Shimadzu group in Kyoto, Japan. All the work that I presented today came from this group, and with their hard work and innovative spirit, we have this wonderful instrument that we can use now in the future for both proteomics and glycomics, and then also to look at drug antibody conjugates. And I feel this is a very valuable technology that could benefit lots of different fields of research. And I hope that you enjoyed the talk and learned a little bit about our multi-digital ion trap. So these are the references for the talk today. And with that, I would like to say thank you, and I'll take any questions.
Great, thank you, Ryan. That was very interesting. So we are open for questions. Anybody can please put them in through the Q&A. The first one came up and got right down to business. What's the ballpark price of this thing?
As far as I understand it at this time, it's between 200 and 250,000. The system itself just comes with actually the Moldy Mini, as you saw in the picture, with two gas canisters, and then there's also a computer monitor in order to operate the instrument.
And I can ask a question or two here. So I know Shimadzu has a whole product line of LCMS instruments. Is there any prospect for coupling your multi systems like this one to some kind of separation up front?
So essentially the separation up front would have to be done offline. I don't believe there's anything in the works to have them coupled together. Typically when we do the upfront processing, it's usually, we'll do some sort of a solid phase extraction and or different methods to do buffer exchange or isolate molecules by affinity chromatography or things of that nature.
Okay, so a question comes up: is there a low mass cutoff in your MSMS, just as there would be in an analog ion trap?
Yes, so the low mass cutoff for the MSMS as well as the MS-3 is about 350 Daltons. And then the low mass cutoff for the MS1 is 650 Daltons.
Okay. The next question concerns mass ranges. I think you gave us two general settings, but can the user set the trap to accumulate a specific mass range?
Yes, I believe it is able to accumulate a specific mass range, whether it be smaller. Originally, when we did the work with some of the data that I showed, we just kind of looked at the whole mass range, but you can dial into specific mass range based on your molecules of interest.
Okay. So here's a timely one. Can it be used for protein pattern recognition? So for example, virus determination?
So that's actually a really good question. I think it is possible. So with the MS1 scan, you would be able to identify viral proteins as long as the virus capsid has been ruptured, and then you're getting good signal, or basically good, if you have a good amount of concentration of the viral proteins. And with that, you would be able to essentially, get a profile of that relates to the virus. Now, in the sense, could you create a database that doesn't have that type of functionality, but would you be able to, let's say, compare it to other ones and then see if they match? Absolutely, experimentally.
The question was brought up, can you do MALDI imaging using this system? I guess that would come down to how quickly you can acquire data.
At this time, the system does not do MALDI imaging. However, it's potentially possible that that might be one of the plans for the future.
Okay. And then another question that occurred to me, are there other ion activation methods that you could employ and maybe do, some top-down proteomics?
Essentially, at this time, it could potentially be possible to do other ionization methods. However, with the system as it is, the ion source is just currently a MALDI. And so in the future—
I was thinking specifically of the activation methods. So, ETD, HCD, all that kind of stuff.
Oh, I'm sorry. I misunderstood what you said. So currently, this only CID is available with this system. So the other techniques, I don't believe there's plans to have those. So ETD, ETD.
Well, that's a very impressive and very compact instrument that you put together there.
Well, thank you.
Yeah. All right, so I don't see any further questions. So if everyone's agreeable, we'll thank Ryan again and move on to the next phase.
Thank you very much.
Okay, so my next duty, and I think it's my last one of the day, but it's